Hello everyone and welcome to my channel. This is an educational channel. We tend to focus on theories of everything and taking deep dives into them, mostly things that you've never heard of before. Today is our 431st video on the reciprocal system of Dewey B. Larson. And the reciprocal system, otherwise known as the universe of motion, is something that Larson derived in the 20th century. In 1959, he put forth his two fundamental postulates stating his case. The first postulate is where most of the assertions are made. The universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. Okay, so we've got motion, we've got space and time, we've got discrete units, and we've got 3-dimensionality. Now, when Larson is referring to motion, a universe made out of motion, made entirely out of motion, he's echoing some other scholars from the past. Other people have said this before, but they weren't able to make their models work. But if you are conceiving of a universe of motion, you have to kind of clear a couple obstacles to be able to accept that. First, you have to be able to accept that motion exists before anything moving. You can have an empty universe with nothing in it, but there's still motion. You have to be able to accept motion without anything moving. You also, in Larson's derivation, he says motion has 2 reciprocal aspects, space and time. So in Larson's universe of motion, he defines motion as the relationship between space and time. It sets up a generalized reciprocal relationship between space and time. Just think of speed. The bicycle is moving 12 miles per hour. 12 miles of space in 1 hour of time. That is speed, space over time. And if you double the speed, then you can say the bicycle is now moving 24 miles per hour. But equivalently, you can also say the bicycle is now moving 12 miles per half hour. So you can multiply the space or you can divide the time. That is a reciprocal relationship. So at least as far as the most basic kind of motion that we can see, there is actually a reciprocal relationship between space and time. Larson spreads that out and applies it to all forms of motion, which he really says are all phenomena. All our scientific phenomena are forms of motion, including matter, energy, force, pressure, electric charge, magnetic flux, permeability, permittivity, solid surface tension, viscosity, momentum. These are all different forms of motion, and they all are different relationships between space and time. Motion is basically a fraction, with space or time as the numerator and time or space as the denominator. But as we will see, space and time come in 3 dimensions. So you not only have space over time and time over space, but you can have time over space to the 3rd power, or space over time to the 3rd power, and so on. Now, the one caveat is that when Larson says that the universe is made out of motion, he's referring to kind of a different kind of motion than what we maybe would normally think of. We generally think of motion in a direction. The car is moving 12 miles per hour north or southwest. But Larson is referring to what he calls a scalar motion. And this scalar motion is a motion that has no direction. You can envision a scalar motion if you take a balloon and you put dots on it and you blow up the balloon. All of the dots will be moving away from each other, but in no specific direction. Each dot will be moving away from each other dot. So basically every dot, and in fact every location on that surface of the balloon, will be moving away from every other. So they are all moving in all directions. The same is true if you contract the balloon and they all move toward each other. So really what you have in scalar motion is you have a direction that is either in or out, but there's no specific direction. It's either really in or out. And if you want to add some depth to your analogy there, you can use something like raisin bread. As you cook the bread, all of the raisins will, as the bread rises, all of the raisins will be moving away from each other. So this is also a scalar motion. And this was also observed in by Hubble back in the day. He determined that all of the distant galaxies were moving away from each other. So this has some astronomical applications that have not been investigated, or people have not figured out the importance of scalar motion to that. And instead they've assigned it to the Big Bang, which imputes a big center point that's not moving at all, that is propelling these galaxies away from each other. That isn't a airtight inference that they're making. Okay, so we have scalar motion, and we have the relationship between space and time. Now, when you have that outward scalar motion of the surface of the balloon, Larson calls that the progression. And then when you have the contracting motion, that would be analogous to gravitation. Now, generally, another obstacle, conceptual obstacle that makes it difficult to get with the reciprocal system is that for thousands of years we have been accustomed to thinking about the universe as a container through which we go through our drama of living in the universe. So we do all of our activity in a background of space and time. We move through this three-dimensional space and, this still three-dimensional space, and events unfold in time. That is not Larson's, not the viewpoint that Larson's universe, posits. Instead of the container universe of space and time, Larson puts forward that space and time are the very contents of the universe. The universe is made out of space and time only, together in motion. And so there is no kind of static background that we're moving through and unfolding in time. What that is it's an abstraction. It's analogous to taking one dot on that expanding balloon and assuming arbitrarily that one dot is motionless. and that all of the other dots are moving with respect to that motionless dot. We call that a reference point. You're assigning a reference point, and then you can start making measurements. You can start determining directions because you've taken the motion out of that one dot and you've nullified that motion that dot's making, and then you can start making sense of the other motions. This is, in my opinion, it's really analogous to like dissecting a frog from your biology class. You're cutting the frog open, and then you're looking at the inside of it as if what you're seeing is remotely the same as what you would be seeing, if the frog was still alive. And so when you're abstracting like that, where you're kind of taking a snapshot of the universe, that's really the container viewpoint of the universe. And Larson, he gives some credence to that with this three-dimensionality. He refers to three-dimensionality, coordinate space, and coordinate time. So in our sector of the universe, we see coordinate space, 3 dimensions of space in a still frame. But we see clock time. We see the clock or time as a scalar magnitude. The clock is always getting later and later and later. It's flowing, it's progressing, but it's not doing so in any particular direction. This is a scalar motion of time at the same time as we have a still framework of space. But if we were in a different sector of the universe, we would observe the inverse of that, the reciprocal of that, which would be three-dimensional time in a still frame and progressing space. Space is always getting farther and farther and farther apart, but in no particular direction, like as on the surface of an expanding balloon, but time is still and three-dimensional. So that he calls coordinate time and clock space. Now, what's also important to understand is that it takes 3 dimensions of space and or 3 dimensions of time just to define one dimension of motion or one scalar dimension. So that reference system is not capable of properly representing reality, which is 3 dimensions of motion. It's only capable of representing one dimension at a time. So there's a limitation to our reference system. Now that may be just the Euclidean aspect of it, which comes out of Larson's second postulate. He postulates a Euclidean universe. And, it seems to me that that's not correct. Bruce Perret, in one of Larson's revisers, also says that Euclidean geometry is not a full description of the reciprocal system, and we need something more inclusive, such as projective geometry, of which Euclidean geometry is a subset. And I would concur with that opinion. So okay, now we get to the discrete unit postulate. This pretty much says that space and time and motion are quantized. You have to have a minimum unit of these things in order to have anything. You can't have a fractional amount or a very small amount, a decimal amount of motion or space or time. You have only discrete units. 1 unit of space is approximately 1/500,000th of an inch. 1 unit of time is approximately 6.5 quadrillionth of a second. So they are very small, but they are existent, and you have to have a full unit before you have time or space. And if you have exactly 1 unit of space in 1 unit of time, remembering that space over time equals speed, then you have what Larson calls unit speed. 1/1 equals 1. This is the progression. Every time with the progression, the universe is progressing 1 unit of space by 1 unit of time. This is the progression. It's a continual, eternal, ceaseless, ubiquitous motion. 1 unit of space per 1 unit of time. And that is also known as the speed of light. Unit speed is the speed of light. And so the universe is expanding or progressing, outward motion of that balloon at the speed of light in all directions. That is what Larson calls the progression of the natural reference system. Also the null point or the 0 point, the origin, the ether of this universe. It's always progressing in that manner. It's omnipresent, and this is the substance upon which the universe is built. It has to be reversed and turned around to create things like matter. Matter is created by reversing that progression and turning it into gravitation, but you have to do it in 3 dimensions, not just 1. If you do it in 1 or 2 dimensions, then you still see that progression at the speed of light. So that is why a photon, which is a partial reversal of that progression, it's still moving outward at the speed of light. But when you finally do reverse the motion, then you begin to start forming atoms and aggregates of atoms. And that's kind of what we're looking at here in the reading for today. We're looking at a book that's called Basic Properties of Matter. And this is about chemistry. Basically, Larson came up with his 2 fundamental postulates, and he then went through a process of deduction from those postulates. If this, then that. If this, then that. And he arrived at a theoretical universe about how the universe would look if his postulates were correct. Then he compared his theoretical universe with that of the empirical scientists, the ones who had done measurements in the laboratory and compiled them in their tables. And for example, this book on chemistry, he compares his findings, his equations, with those of the legacy scientists in chemistry. So things like the melting point and the specific heat, the compressibility. That's what we're looking at today, is the compressibility. And so it's an interesting study, and we're going to see how Larson is able to arrive at the same kind of results that the scientists do in their observations, strictly from theory. Now, one other thing about the discrete unit postulate is that what this does is it sets up, as the speed of light outward in all directions is the midpoint of the universe, it sets that up as a boundary between 2 dissimilar regions, 2 reciprocal regions. One he calls the cosmic sector, that's moving faster than the speed of light, and the other is the material sector, that's moving slower than the speed of light. The material sector is really the only sector that we're familiar with, and this material sector has coordinate space and clock time, 3 dimensions of space in a still frame moving through time. But if we cross that unit speed boundary and moved into the cosmic sector, what he calls the cosmic sector, then we would see coordinate time and clock space, 3 dimensions of still time moving through space, progressing or flowing through space. So there's an inverse relationship there. We have to reverse the interchange the functions of space and time. But within each one of these sectors, there is also a subsector which is bounded by the unit space or unit time boundaries. Okay, so there's 3 boundaries. There's a unit speed, unit space, and unit time. If you don't have a full unit of space, such as an atom that's interacting with another atom at close range, then you don't have a full unit of space. And if you don't have a full unit of space, then you only have time, because space and time are the contents of the universe. It's got to be one or the other or both. If it's not space, it has to be time. Larson refers to this as the time region. And in the time region, again, the rules reverse. So this region, time region, which is where atomic and molecular interactions occur, you reverse the roles of the progression and gravitation. So now within the time region, the progression is bringing everything closer together in space, and the gravitation is bringing everything further apart in space. But I thought you just said that there was no space. Well, that is true. In our sector of the universe, we are anchored to the spatial reference system. So we only see space. We don't see time. What goes on in the time region is occurring in time, but we see it as the inverse of what's actually happening because we only see space. Larson calls this equivalent space. We see only, we see the spatial effect of time in equivalent space. And there are some things that we have to reduce. That he calls it the interregional ratio, and then equivalent space is a 2-dimensional zone. So we also, basically are seeing a 2-dimensional projection, or I'm not sure what the word would be, of what is actually going on. So we're not seeing what's actually happening. We're seeing its equivalent in space. And the interregional ratio is the fraction by which you have to reduce those findings of what you're seeing, because you're not seeing everything that's actually happening. You're just seeing a small fraction of it, or what you're seeing has to be reduced. And these things play a factor in Larson's chemistry determinations. The same thing is going on in the cosmic sector with roles of space and time reversed. So if you don't have a full unit of time, then everything happens in space. Larson calls that the space region. That's the realm of cosmic atoms and cosmic molecules interacting. And those are also known as antimatter. Okay, we're going to try to read a little bit from Larson's chapter here on compressibility. Larson just determined this equation for figuring out the initial pressure. There's an initial pressure, and there is an external pressure. The initial pressure is coming from the progression that's already there, the intrinsic or pre-existing pressure. And he determined through deduction this equation: the initial pressure equals AZY, which are three numbers that have to do with the rotations of the atoms, or the gravitation of the atoms, that are basically the rolling back of the progression that enables you to move from that expanding balloon to the contracting balloon of gravitation. That is what creates matter. Larson's periodic table is based on these numbers, these 3 separate numbers: 2 2-dimensional rotations and one dimensional rotation in the opposite direction. So he's got these AZY numbers, which are related to those numbers from the periodic table, Larson's periodic table. And then he puts that over the interregional ratio times 6 times the natural unit of space to the third power. He derived that in yesterday's episode. Okay, so the value derived from this equation is the magnitude of the internal pressure in terms of natural units. To obtain the pressure in terms of any conventional system of units, it is only necessary to apply a numerical coefficient equal to the value of the natural unit of pressure in that system. This natural unit was evaluated in Volume 1 as 5.202 trillion dynes per square centimeter. The corresponding values in the system of units used in the reports of the experiments with which comparisons will be made in this chapter are 15.54 million atmospheres, and that is also equal to 16 million kilograms per square centimeter, or 15.75 million megabars. In terms of the units used by Bridgman, the pioneer investigator in this field, in most of his work, the equation that we just derived takes the form of the internal pressure equals 17,109 AZY over the cube of the interregional ratio, which was derived in the previous two chapters, and that label is kilograms per square centimeter. The internal pressure, thus calculated for any specific substance, is not usually constant through the entire external pressure range. At low total pressures, the orientation of the atom with respect to the line of the progression of the natural reference system is determined by the thermal forces, which, as we will see, favor the minimum values of the effective cross-sectional area. In the low range of total pressures, therefore, the cross-section is as small as the rotational displacements of the atom will permit. In accordance with Le Chatelier's principle, a higher pressure, either internal or external, applied against the equilibrium system causes the orientation to shift in one or more steps toward higher displacement values. At extreme pressures, the compressive force is exerted against the maximum cross-section. 4 magnetic units in one dimension and 8 electric units in another. That is the maximum cross-section. Similarly, only one of the magnetic rotational units in the atom participates in the radial component Y of the resistance to compression at the low temperatures, at the low pressures. But further application of pressure extends the participation to additional rotational units, and at extreme pressures, all of the rotational units in the atom are involved. The limiting value of Y is therefore the total number of such units. The exact sequence in which these two kinds of factors increase in the intermediate pressure range has not yet been determined. But for present purposes, a resolution of this issue is not necessary, as the effect of any specific amount of increase is the same in both cases. So in general, I have to say I didn't understand very much of that, even though I've read it over and over again. But basically, the progression is generally constant. And so what you have to establish an interatomic equilibrium is you have to balance the progression, which is constant motion inward in the time region in space, and gravitation, which is based on an inverse square law. So at the place where those are equal is where you have this interatomic distance. In Larson's system, there is no such thing as a nucleus. The so-called nucleus is actually the entire atom. And so in Larson's system, atoms find an interatomic equilibrium in which they pack together with other atoms, and there's a distance between them. Whereas in legacy science, atoms in the solid state are basically packed together, touching each other. In Larson's system, there is a distance between them, and that can be raised or lowered by the pressure to a significant degree. Now, here he's kind of varying the initial pressure or the progression. So even though the progression is constant, it doesn't appear constant because depending upon the level of pressure that is being exerted, different amounts of the atom become involved. And so the equation has to be adjusted, or the reckoning has to be adjusted. So in the low range of total pressures, therefore, the cross-section is as small as the rotational displacements of the atom will permit, in accordance with Le Chatelier's principle, which I cannot remember what that is. I'll try to figure that out. He probably will. I know he mentioned it in something I was reading recently. But so anyway, again, this is a lot like detective work. You have to pick it up one piece at a time, and you have to go really slow and reread, and it doesn't seem like you're making progress, and it seems like everything is complicated, but it really isn't, because it's much simpler than the legacy system of science, because it's a generalized system. And so if you understand how it works in one area, you understand other areas. In the scientific curriculum, science and social sciences and liberal arts, you have a different set of rules for every subject. Larson applies the same rules for every subject, so you just have to learn it once and then learn how it applies. Okay, thanks. We'll tune in.